Let's look at the first question. L, M, N are the p term, q term and r terms of a GP, all positive. Then determinant log L P1, log M Q1, log N R1 equals to first option -1, second option 2, third option 1, fourth option 0. Now L, M, N are given to be p term, q term and r terms of a GP. Let A be the first term of the GP. First term of GP, and R is the common ratio. Capital R is the common ratio. Let's take capital R because we already have a small r there. Let is the common ratio. Then L is the pth term. So Tp is L. L is Tp. T for term, p term, that's equal to A into R power p minus 1. Similarly, M is equal to A into R power capital R power q minus 1. And N is equal to A into capital R power R minus 1. So when I go for logarithm of L, log L will be log A plus p minus 1 into log R. P minus 1 into log R here. Okay. Similarly, log M will be log A plus q minus 1 into R. And log N is equal to log A plus R minus 1 into log R. Okay. Now let us put all these things in the determinant, and then what you have here is the determinant becomes log A plus p minus 1 into log R, and then p 1. Similarly, log A plus q minus 1 into log R, q1, log A plus R minus 1 into log R, R1, 1 here. This determinant is to be evaluated. Now observe that in this column we have two parts, this log A and this p minus 1 into log R, q minus 1 into log R, R minus 1 into log R. We can split this determinant into two determinants. You split this determinant into two determinants, keeping the other two columns fixed. So p, q, R 1, 1, 1 fixed here, p, q, R 1, 1, 1 fixed. Now what will be the first column here? Log A taken. Log A can be taken out and we'll have 1, 1, 1 here. Similarly, we'll get p minus 1 into log R, q minus 1 into log R, R minus 1 into log R here. So log R will be coming common out. So we'll have p minus 1, q minus 1, R minus 1 this way. Clearly, this determinant is 0 because two of the columns are identical. Column 1 and column 3 being identical, we have the determinant to be 0. What about this? We have here, if you observe that if you subtract a column from another column in a determinant or a row from another row, the determinant is invariant. It doesn't vary. So here C2 minus C1 will make 1, 1, 1 here. So if I go for C2 minus C1, that is column 2 minus column 1, I will get p minus of p minus 1. So these two columns will become identical, 1, 1, 1, 1, 1, 1 and p minus 1, q minus 1, r minus 1. So which means that the determinant also becomes 0. This part also becomes 0. Log r into 0, this log a into 0, the entire determinant is equal to 0. Therefore, the right option is 4. Option is 4 there. If a is positive and the discriminant of ax square plus 2bx plus c is negative, then the determinant First row a b ax plus b, second row b c bx plus c, third row ax plus b bx plus c 0 is first option positive, second option equal to ac minus b square into ax square plus 2bx plus c, third option negative, and fourth option is 0. Okay, let's look at how to go about this problem. We are given that ax square plus 2bx plus c has discriminant to be negative. So discriminant of this is given to be negative. What is the discriminant? 2b whole square minus 4a into c. That makes it 4 into b square minus ac. So this is 4 into b square minus ac, and that is negative. Negative here. Okay. So that means bc minus a square is negative or ac minus b square is positive. So we'll have, that will be one of them may be used in that determinant. So now let's look at the determinant AB. See some pattern here. AB, ax plus b, bc, bx plus c. Here ax plus b, and then bx plus c, 0. Now what we do is, determinant is invariant of row operations of the form Ra being replaced by Ra plus k times Rj. We know this. That is, if I operate, let's go for an operation here. We will multiply the first row with x and the second row with 1 and just add up. So that you will get ax here and b here, and then you can subtract that from the row 3. So row 3 minus x times row 1 plus row 2. Let's go for this. X times row 1 plus row 2. So what is that going to give us? That will give us a, b, ax plus b, b, c, bx plus c, and here when I am going for this, this part will be 0 because I am multiplying this with x, so this becomes ax, and you are adding a b to it. The second row is being added up, so ax plus b, and that is being subtracted here, so we get 0 there and we get 0 here. And now what happens here? We multiply this with x and then this as it is, and 0 from 0 we subtract it. So what do you get? Minus ax square plus 2bx plus c. Okay. So this is the determinant here. Now I'll open up this determinant and see what is it we get here. We have the determinant to be, I open up the determinant by the last row. If I open up the determinant by the last row, what do we get? We get minus of ax square plus 2bx plus c into ac minus b square. AC minus b square. So that makes it, that is this element into its cofactor, corresponding cofactor. So rest of the elements being zeros, I'll not have that part. So what do we have here? B square minus AC, I'm absorbing this minus sign here, into ax square plus 2bx plus c. Okay. Now going by the options, the first option said it's positive. Can we say anything about it? B square minus AC is negative. And we are also given that the discriminant of ax square plus 2bx plus c is negative and a is positive. So what does that mean? It will be totally positive. Okay, so this b square minus AC plus, this is negative, negative into positive, this is positive. So that cannot be positive throughout. So what is the right option? It's clearly, this is negative, we know, and this is positive for all x, we know. How do you say it's positive? We are given that the coefficient of x square is positive and the discriminant is negative. So the graph of ax square plus 2bx plus c will look like this. So that is always positive. Whenever the discriminant is less than 0 and a is positive, the graph of ax square plus y equal to x square plus 2bx plus c will look like that. So it is always positive, and this is positive for all x. B square minus ac by choice is negative, so the product is negative. So the right option is answer 3. Let's move on to the next question. If determinant a square 1 plus a cube, b square 1 plus b cube, c square 1 plus c cube is equal to 0, and the vectors 1 comma a square, 1 comma b square, 1 comma c square are non-coplanar, then the product ABC equals to, first option being 2, second option -1, third option 1, fourth option being 0. So let's have a look at this thing. Now we are given that this determinant a square 1 plus a cube, b square 1 plus b cube, c square 1 plus c cube is 0. This is given. What else is given about ABC? We are also given that the three vectors 1 comma a square, 1 comma a square, 1 a square, 1 b square, 1 c square, these three vectors are non-coplanar. Non-coplanar. The condition for three vectors to be non-coplanar is the box product of the three vectors should be, we'll call this as vector v1, v2, v3. The box product should be non-zero. So v1, v2, v3 should be non-zero. In other words, this is equivalent to saying, what is the box product of the three vectors here? 1 a square, 1 b square, the determinant followed by this 1 c square. This is non-zero. So this is what is given to us. So how do we use this part and this determinant being equal to 0 to get the value of ABC? Let's see how that can be done. Let's observe that the third column is having two elements in each row. So it's a sum of two elements. We shall split the determinant. We shall split the determinant into two determinants here, keeping the other two columns as it is. So this determinant becomes two determinants here. It gets split into two parts. What is it? A, B, C, A square, B square, C square, 1, 1, 1 plus. Now keeping the other two columns as it is, we'll have the other part of the third column, A cube, B cube, C cube, A, B, C, A square, B square, C square. And this determinant is given to be 0. Right hand side, I'm just copying. Now observe that you could take a common from the first row and B common from the second row, C common from the third row. So then this determinant becomes A from the first row. So if you take out A from the first row, what is it? What does A become? First row become 1 comma A square. You can take out a B from the second row, so B out. Then you have 1B, B square, and then 1C, C square. So ABC. Now, okay, just make an observation here. How are these two determinants? Are these two determinants same? Observe that with two column interchanges, column 1 with column 3. So you will have 1, 1, 1 here, ABC here. Then, but ABC have to come into the middle. So we will go for one more interchange, column 2 and column 3. That makes it but each interchange of a pair of columns will give rise to a sign change in the determinant. So if you go for even number of sign change, even number of row interchanges or column interchanges, we're going to end up with the same determinant. So what we have is, this will be also same as 1 1 1. So minus 1 square I'm saying, because each time I had gone for two interchanges, column 1 and column 3 have been interchanged, and column 2 and column 3 will be interchanged, and each interchange will give rise to a minus 1. So I'm writing minus 1 square, 1 1 1, ABC, A square, B square, C square, A square, B square, and C square here, C square here, B square and C square. Now this entire thing is equal to 0. Observe that this part is non-zero. I mean, you can take this common and you have something 1, the determinant 1 1 1, ABC, A square, B square, C square, taken common into 1 plus ABC is equal to 0. Now observe that this is non-zero. Why is it non-zero? Because the vectors v1, v2, v3 are non-coplanar. Therefore the box product of these three vectors will be non-zero, which is nothing but this determinant will be non-zero, and we have made use of that fact. So we have, therefore this implies ABC is equal to minus 1. So this being non-zero, this has to be obviously 0. So ABC will be equal to minus 1 there. A into B into C is minus 1. Okay. So the right option is answer is 2. So the key point that we've made use of is that, first of all, how to handle this determinant? You can split it into two determinants. One more thing that what we are given is that these three vectors are non-coplanar. So what is the condition for non-coplanarity of three vectors? The box product should be non-zero. What is that box product? It is this determinant. Just write the components along the rows and form a 3 by 3 determinant. You get that to be the box product. Box product is non-zero, and we have therefore ABC to be equal to minus 1. So that's the answer. Question number 4. If the system of linear equations x plus 2ay plus az equals to 0, x plus 3by plus bz equals to 0, x plus 4cy plus cz is equal to 0 has a non-zero solution, then A, B, C are in what type of progression? Arithmetic progression, geometric progression, harmonic progression, or they satisfy the equation A plus 2B plus 3C equal to 0. So let's see how do we go about this equation, this problem. Now we are given that the system of linear equations, I'll put that in the matrix form. Here 1, 2a, I'm writing the coefficient matrix A, and then 1, 3b, b, 1, 4c, c, this into x, y, z equals to null matrix. Now this is the way we write the system of linear equations in the matrix equation form. Now when you have a system of homogeneous system of linear equations, it will always have a zero solution. When will it have a non-trivial solution? It will have a non-trivial solution when the number of equations is equal to number of unknowns. We can say that if the determinant of the coefficient matrix is 0, then this system is going to have a non-zero solution. What do you mean by non-zero solution? At least one of the x, y, z being non-zero and the equations being satisfied, such a solution we call as a non-zero solution. Zero solution would mean all x, y, z being zeros. Now we are interested in a non-zero solution. A non-zero solution would mean at least one of the x, y, z not equal to 0, satisfying the equations here. Okay, so here therefore we have to, the determinant must be 0. Determinant of the coefficient matrix must be 0. So Ax equal to 0, A some n by n matrix, A is some n by n matrix, n by n, has a non-zero solution if and only if determinant of A is 0. Determinant of A is 0. Okay, so we'll go use this result here. So now the determinant has to be 0 then. This has non-zero solution given. So given that this is given has a non-zero solution. So we use this result. So from the result, what is it you can say? We can say that this determinant has to be 0. Determinant of the coefficient matrix. So let's look at 1, 2a, a, 1, 3b, b, 1, 4c, c must be 0. Now let's go for, we can open it up as it is, but let's see. I'll make these two entries 0 by some simple suitable row operations, R2 minus R1 followed by R3 minus R1. Let's perform these two. These two are invariant operations, we know. So 1, 2a, a, and then 0, we get 3b minus 2a, b minus a, and here we get 0, 4c minus 2a, and then c minus a is 0. This is 0. This implies this is 0 using these operations. This determinant is same as determinant, so that's 0. Now let's open it up. Let's open it up by the first column. So when you open it up, you get 3b minus 2a into c minus a minus b minus a into 4c minus 2a, 4c minus 2a equals to 0. So what are we getting from here? With some manipulation, I mean just a simple calculation, we will find that we'll get b to be equal to 2ac by a plus c. Now with some simple manipulation, we will get b to be 2ac by a plus c. Now what does that mean? A, B, C are in harmonic progression. This implies A, B, C are in harmonic progression. Okay. So after a few steps, we will get that B is equal to 2ac by a plus c, which in turn implies that A, B, C are in harmonic progression. So this is the methodology that what we are using is, the key thing is that a key result that we are using is that whenever you have a system of linear equations, homogeneous system of linear equations with A being coefficient matrix being a n by n matrix, it has a non-trivial solution or a non-zero solution if and only if determinant of A is 0. So given that it's non-zero, has a non-zero solution, determinant should be 0, and from that we can easily obtain that B is equal to 2ac by a plus c, which means that A, B, C are in harmonic progression. So the answer is 3. If 1 omega square are the cube roots of unity, then the determinant 1 omega power n, omega power 2n, omega power n, omega power 2n 1, omega power 2n, 1 omega power n in the third row is equal to first option 0, second option 1, third option omega, fourth option being omega square. Let's see how we handle this problem. Now first of all, 1 plus omega square is 0. Let's recall some properties of the cube roots of unity. Omega power 3 is 1, which in turn implies omega power 3n also is 1. N is any integer there. You can raise it to any integer and you get 1 there. Now observe that in the determinant 1 omega power n and 1 omega power 2n, omega power n, omega power 2n, and we have here 1. Third column has omega power 2n, which we can write it as omega power n into omega power n. This second row element here in the third column has 1 which I can write this as omega power 3n. Again we'll split it up as omega power n into omega power 2n. And then we have omega power en. Observe that if you multiply the second column with omega power n, you are getting the third column. So there is a column dependency. So that means this determinant can easily be made 0. So what is it? You can go for column 3 minus omega power n into column 2. So that will make it entire third column to be 0. So now if one column is 0, no matter what may be the entries of the other columns, the determinant will have to be 0. Therefore this determinant is 0, and hence the answer is 1. Let's move to the next question. Let A be the matrix 0 0 minus 1 0 minus 1 0 minus 1 0 0. The only correct statement about the matrix A is, first option, A is a 0 matrix. Second option, A square equal to I. Third option, A inverse does not exist. A is equal to minus 1 into I, where I is the unit matrix of order 3 by 3. See, looking at the options, it's clear that A is not a 0 matrix, so option 1 is ruled out. Next, it may be the second option, A square is equal to I. Okay, let's see. Let's multiply A with A. What is A square? A multiplied with A. So 0 0 minus 1, 0 0 minus 1 here, 0 minus 1 0, minus 1 0 0. What is A square here? The first row with the first column, what do you get? 1. First row with the second column, you get 0. First row with the third column, again 0. Second row with the first column, you get 0. Second row with second column, you get a 1. And you get a 0 here, 0 0 1. Clearly A square is I, 3 by 3 identity matrix. So option 2 is clear. Actually, if A square is I, it's simple that A into A is I, which means that A is invertible. So option 1 cannot happen, option 3 cannot happen, and clearly A is not equal to minus 1 into I. So the fourth option is also not true. Clearly A square is equal to I. So we can say that option 2 is correct. Answer 2 is correct. So let's move to the next question. Let A be equal to 1 minus 1 1, 2 minus 2 1 minus 3, 1 1 1, comma, second matrix 10 into B is equal to 4 2 2 minus 5 0 alpha 1 minus 2 3. If B is the inverse of the matrix A, then alpha is first option minus 2, second option 5, third option 2, fourth option is minus 1. So let's see. We are given that A and B are inverses of each other. So A into B is I. Now when you multiply A with 10B, you are given A into 10B. Let's consider this. What is that going to be? It's going to be 10I. That is 10 0. We'll write it later. So what is A into 10B? A is what's given? First row is 1 minus 1 1, and second row 2 1 minus 3, third row 1 1 1, 4 2 2, minus 5 0 for alpha, 1 minus 2 3. That should be equal to 10I. So 10 0 10 10 here, and rest of the entries being zeros. That's 10I. So this is what we have here. Okay. Now just open it up. I multiply the two matrices and then equate. So it's a simple thing to do. 1, 4, 4 plus 5, 9, 9 plus 1, 10. That's matching. 10 and 10 are matching here. And actually want this element. So let's involve directly this column. When I multiply with the first row, what is it I get? 1 into 2, 2, 2 minus alpha plus 3. So 5 minus alpha. I make it 0 here, and this has to be equated to this 10, 0, 0. So obviously this 5 minus alpha has to be 0 there. So 5 minus alpha is 0 here. Alpha has to be 5. So we don't have to multiply the entire two matrices. Straight away we are able to see that alpha has to be equal to 5. It will anyway comply with the other entries. Okay, so it's enough if I just look for how to obtain that value of alpha. Okay, the answer is therefore 2. Let's move to the next question. Question number 8. If a square minus a plus I is equal to null matrix, then the inverse of a is what? A plus I, 2 a, third option a minus I, fourth option I minus a. Now it's a simple thing. A square minus a plus I is equal to null. So what is it you can say? We can write I to be equal to a minus a square. That is a into this. A can be written as a into I. So a taken common, I minus a, distributivity. Now a into some matrix is giving rise to I. I is equal to a into I minus a. So clearly it implies that A inverse is equal to I minus a. That is the right option. So answer is 4. If A and B are two square matrices of size n by n, such that a square minus b square is equal to a minus b into a plus b, then which of the following will be always true? A is equal to b, ab equal to ba. Third option being either a or b is 0 matrix. Fourth option is either of a or b is an identity matrix. Let's look at this. You are given a square minus b square to be equal to a minus b into a plus b. Now what is it? Let's open up this product. A into a plus b minus b into a plus b using distributivity. What is this equal to? A square plus ab minus ba minus b square. Now when can this be equal to? We can cancel out this a square and we can cancel out left additive inverse of a square. We can cancel out this minus b square is cancelled. So you get a null matrix here. So AB minus BA is a null matrix, that is AB is equal to BA. So from the given condition a square minus b square equal to a minus b into a plus b, we are able to conclude that AB is equal to BA. A equal to B is, if A is equal to B, it may happen, but that is not going to be a necessary condition for that to happen. So a square minus b square equal to a minus b into a plus b will not always imply a equal to b, right? But if a is equal to b, that condition will be true. So the first option is not to be taken. Second option is clearly seen on the board, right? Third option also, it is not necessary. That is, if a or b is 0, it is sufficient to say that a square minus b square is equal to a minus b into a plus b, but that condition is not a necessary condition for that equation to be true. Similarly, is the fourth option also cannot be true. So the right option is, answer is 2 there, answer is 2.